In this segment, I want to get into Wii RAM hacking. Now, I've covered the USB Gecko in previous segments. If this is the first time you're hearing about it, it is a device that was created for the GameCube and the Wii that plugs into the memory card slot and allows you to have a USB interface to do various debugging and development features. It's really great for homebrew, and if you have a real interest in any of the GameCube or Wii homebrew, I'd highly suggest getting one. Now, before we even begin, we have to have a slight understanding of the inner workings of the Wii. The Wii itself has 88 megabytes of memory. Only 24 of those megs we're really interested in. The Wii does partition the memory into a Mem1 and Mem2 range. I'll put some links in the show notes that explain the memory ranges of the actual Wii itself. I'm not going to get into it today. But you have to understand that there are certain ranges of addresses that if you poke at it, it'll instantly crash the Wii. Reason being is that the Wii does have encrypted parts of RAM. There are two main CPUs inside the Wii itself. You have the Starlet, which when you first power up the Wii, it sets up all of the communication, the encryption, it sets up the controllers, it sets up the entire environment, and then makes sure that everything is a secure session, everything is encrypted throughout the AS and back again, and it puts itself into small ranges of memory. Now, once everything is authenticated and secured, it hands control over to the Hollywood CPU, and the Hollywood CPU will execute the code and let you play your game or your homebrew. Now, the problem with this is if we actually read or write to any of the contents of RAM that the Starlet's execution code is in, or is residing in, or any encrypted RAM for that matter, it'll instantly lock up the game. Also, you can peek into not only the actual RAM for the system RAM, but you can also poke into the graphics RAM. So sometimes a game might be using system RAM to hold graphics data, and just by reading it, causing that lag, when you dump the data, it's going to crash the system. So when you first get started, do a lot of research on the USB Gecko forums. There's a whole community of RAM hacking people behind this, and they've got a lot of great information already out there. I'm going to link to them, I'll put it in the show notes. Now, before we even get into the actual console side, we have to understand object-oriented programming languages. Now, typically with NES hacking, the game itself actually resides on a flash cartridge. Everything is all in that one area. And we always know that the RAM addresses are always going to be the equal no matter what, no matter whenever we load a stage or wherever it's going to be, everything's on that media. But today, games are held on CDs or DVDs. There's no way to put like a 700 meg CD in the contents of only 88 megabytes of RAM. So when we have a 3D game, it's what we call an object-oriented language, meaning everything in the entire game is considered an object. Like an example, let's say that my entire room here is a computer simulation. My remote control is coded and compiled as one object. My laptop here is one object. I am an object. The camera is an object. The tripod stand, an object. My tables, they're objects. Those objects will load into memory, and in those objects themselves will contain actual memory locations. Now, when the game's loading things in the memory, today we're going to focus on Super Mario Galaxy for obvious reasons, and I'll explain it a little bit. Now, when the game is actually loading in the memory, the first thing that should load is the stage. So sometimes the stage could be 5 megs, maybe it could be 10, maybe it could be 50. You don't know until it loads. So when Mario finally, which is going to be the obvious character you want to have your attributes for, when Mario loads into that level, the memory addresses in which his health and his lives and star bits and coins will never be in the same location twice. This is an obvious thing for any object-oriented language, because when things load into memory, it goes first in, first out, or what's called FIFO. And the FIFO buffer basically means is the first thing that goes into the RAM is the first thing that comes out of the RAM. So the first thing that goes into the RAM is going to be the level. So if the level takes up, say, 10 megs of space, and then Mario takes up, as an object, takes up 1 meg, he's going to be at the 11 megabyte mark. But what happens if your level takes up 15 megs? Mario will start at the 15 meg limit and take up 1 meg. Argument's sake, I'm just trying to make this easy. So this is where pointers come in. Now, the first thing that really loads to RAM is what's called a pointer list. So think of it like this. If a game is compiled as an object, and each object is like a book perhaps, where there are chapters, you might not know where those chapters are unless you manually look through. But if you look at the index of the book, it'll tell you where all of the chapters start on what page numbers. That's what a pointer is. The pointers are an actual list of where the actual object will reside in RAM, and where in that object file, in a memory offset, where to actually find specific values like health, coins, what power-ups you have, and a whole bunch of stuff. So typically with the NES RAM hacking I've done like 20-something segments ago, we just basically would dump the RAM and we'd compare and contrast, and we'd look for different values, differences in values, like, you know, more than, less than, equal to, not equal to, specific values and such. So go back to those segments and check out the basic techniques for RAM hacking. Those will be applicable to this. Today, I'm going to get a little bit more in depth. I'm going to automatically understand that you have a clear understanding of binary, hexadecimal, as well as the decimal numbering systems, 8, 16, and 32-bit string formats and variable formats. I'm automatically going to assume that you know the basic concepts of how to dump the RAM, use a utility to compare two sets of RAM to find the differences, to find the addresses you're looking for. All of that I'm going to assume you already know. If you don't, hit previous episodes. I'll put links in the show notes on basic concepts of that. So we're going to go and load up Mario Galaxy and the Gecko OS, and we're going to get to the PC side and get to a brief tutorial on how to start Wii RAM hacking using Super Mario Galaxy. Go ahead and load Gecko OS by way of choice. I plan on using the Wii Homebrew channel, and launch the weird graphical user interface. It'll automatically launch the game. So, brief overview of what you're seeing in front of you. The interface has the next step and run button. Once the game actually loads, you can either hit next to go and increment one CPU cycle, or you hit run to resume the actual game itself. If at any time you need to pause the game because you're in heavy action or just whatever reason need some time to think, you can go ahead, hit the pause button. Top left, we have the memory ranges that we're allowed to play in, which I'll put some links in the show notes about. And it also automatically fills in the start and end addresses that are safely allowed to actually play in. Now, we can actually do a search of a value type of an unknown value using, you know, the particular equal, not equal, less than or equal, you know, the typical, you know, compare types. Or we can actually load, we can search for specific values of either 8, 16, or 32-bit values. Later on, we'll be using the pointer search, the memory viewer, as well as the GCT codes, but we'll get into those when the time comes. Go ahead and load up Mario Galaxy and get to the primary observatory place. And if you notice on the screen, I have 9,852 star bits, so we're going to go and start searching for things. So we're going to search for a 32-bit value of 9,852. Now, of course, this is in decimal, and we want to work in hex, so we hit the convert decimal to hex button, and it'll convert it to 267C. We're going to go ahead and start. It'll take about 45 seconds to dump 24 megs of data, and the Wii is going to lock up, it's going to freeze and make a horrible bunch of noise, so mute your TV, and then just bear with us. Alright, the search is done, and we are left with only 6 codes, which is pretty good. Every once in a while you'll have a couple of tens of thousands. So we're going to go ahead and we are going to use 2 star bits, and we are going to put in the number in decimal, 9,850. We're going to convert that to hexadecimal, and we're going to search again. Okay, we're only down to 1 address, so when you get down to a couple of addresses, it's time to do some nitty-gritty poking around. You can right-click the address, and then manually hit poke. Later on, we'll be using the memory viewer, pointer 1 and pointer 2, but for now, we're going to poke. And if you'll notice, it's at the previous value of 267C, so we're going to go ahead and poke it. And there we go, it actually goes up. Bring it back down to A. There it goes. Fine and dandy. It goes to show that now you can poke this specific memory address as a 32-bit value. So now that we can go to the GCT codes, and we're going to make a new code. And we're going to name this code, if it lets me rename it, Starbits. And going to the USB Gecko's website, they actually have an in-detail tutorial on how to use, or actually an explanation, I should say, it's not much of a tutorial, on different memory ranges, base addresses, pointers, registers, such and such and such. So, right now we're actually interested in locking a 32-bit value at an address, at a base address. So, let's see, this is 16, no, we want 32. So, alright, so our prefix is going to be 04, which means to write 32 bits into the RAM of the base address. Alright, so we'll go back to the weird graphical interface, and I've actually already put together this code. Where did it go? I do believe it's this one. Give me 1 second. I'm just trying to copy and paste here. Here we go. Let me make sure that these are proper addresses. F6, 3C, F4, 36, alright. Alright, so 04 is the prefix saying, as stated, 04 is 32-bit RAM write at the base address, and we found the base address quite easily. And the base address being F6, 3C, F4, and we want to lock it to the value 270F, which should constitute as 9,999. So we're going to add the code to the star bits, and then we're going to enable it. Hit enable, and we're going to apply the codes. And there we go. Our first code. It's going to lock the star bits to 9,999. So once this is done filling up, I'll actually show. There we go. Doesn't matter how many you use, this code is going to automatically lock this base address and fill it with a 32-bit value, decimal 9,999, or hexadecimal 270F. So this is our first basic search. Alright, all fine and dandy, now we know how to find base addresses, but what about these elusive pointers that I was talking about? So we're just going to go ahead and fly to any random galaxy that we can start doing searches on pointers. Now, to get a pointer, we're going to have to load up 2 separate worlds, and we're going to have to find the same, a different address for the same thing. So the easiest thing to look for is health. So we're going to go ahead and restart everything, reset all of the values, and we're going to start on Mario's health, and we want a 32-bit value for decimal 3, 32-bit 3, because we know he has 3 health right now. We're going to go ahead and do a quick search. Alright, so we're down to 5,707. That's a bit, so we're going to lose a bit of health, and you can use the typical compares of equal, not equal, greater than, less than, but we know the value is at 2, so we're going to search again for 2. Alright, we're narrowed down to 6, but I'm a stingy bastard, so let's try to get this down to a few less. Reduce the health by 1, and search again. Now that's more like it. We're down to 2 addresses. Now we're going to go ahead and poke. We'll poke this first address, and every time we poke it, we notice that the life meter on the screen just jiggles, so that's obviously not it. We'll poke the other address. And we've got it. And we'll make this 3, bring Mario's health back up to 3. Verified that this address for this world is Mario's health. But if we change worlds, because of the way object-oriented programming works, it won't be the same for another world. So we need to find a pointer. So we're going to enter this address into pointer search 1. And if you sorry, let me narrate. You right-click, and you go to pointer 1, and go to the pointer search, and you'll notice that it'll enter in address 1. Then go to the memory dump, and do 1 memory dump for this stage. Alright, once the memory dump is done, I've noticed a small problem with the weird interface. You actually have to go and click File 1, and manually point it to the actual dump180.bin. Now, we've manually found the address for Mario's health for this level, and we've entered that address into the pointer search. Now we have to go off to another level so we can find the alternate address for another world so we can compare these two different files for pointers. Alright, we're going to go and fly over to a separate world because, like I said, when it comes to object-oriented languages, things don't always go into memory the exact same time twice. So, we've got the previous memory address in memory, and we're going to go and try to poke it at 02. And if you notice, Mario's life isn't going down. Like I said, because of the object-oriented language, we can't always use the same address that we find in the world. We need to find the pointer. So we're going to go and, again, look for Mario's health, and it's going to be decimal 3, as well as hex 3, and we're going to be in the 80 memory range, and Weird automatically puts in the safe ranges that we're allowed to play in, and we're going to do a preliminary dump and see if we can find the memory address of Mario's health for this specific level. Alright, well that narrows it down to about 7,296 possible values, so I'm going to go get hurt. Come on. Now we know his health is down to 2, and we'll do this again, do another search. Alright, so we're down to 3 values, so I'm going to assume that this last value here is going to be it, because that's how it was the last time. I'm just going to make an assumption. We're going to go ahead and poke it. And there's Mario's health. Alright, we're going to bring it back down to 2, just to verify. Alright, bring it back up to 3. And then we're going to enter this into pointer 2. Now, this is the address for the Mario's health in the first level, and this is the second level. This is the binary dump from the first level. We're going to do a binary dump of this level. Alright, once it actually resumes, you manually have to go and tell it exactly where the files are. It's a little glitch that's in the weird interface. That'll hopefully be fixed sometime soon. And then hit your search button. And what it's going to do is it's going to manually compare both of these binary files as well as the addresses that you specified to actually look for possible pointers as well as their offsets. So we've got a couple of results and a couple of best results. And we'll take a further look into this right now. Alright, I just moved Mario over to a nice safe spot so he can't get hurt and nothing else in the variables can change. And I've already done some poking around previously, and we're going to go ahead and look at this 806B7B40 pointer address. And we're going to copy this. And notice how it has this plus 380. That's telling us the offset. So it's telling us that within this memory address, and this pointer and offset should contain Mario's health. So we're going to go to that memory address. This memory address is leading us to another memory address. So this is the pointer. And this is where the pointer is leading to. And the pointer is leading us to 810B2ED0. So we're going to copy this down, and we're going to load up calculator. Good old calculator. And for those of you who don't know, you can hit the View button and go between Scientific and Standard View. We're going to go into Hex, and we're going to paste in using Control-V to paste and Control-C. Don't know if too many of you know about those shortcuts. And we're going to add, in Hex, 380 as the offset. And we're going to come up with this new address of 810B3250. And we're going to Control-C to copy this, and we're going to go back to the weird interface. We're going to put this in the memory viewer. Actually, you know what we can do is we can just poke it. Let's just do that. Control-V. And we'll poke it. Poke this as 2. And look, Mario's life goes down. We'll poke it as 3 again. So, if we go to the memory viewer, Control-V, there it is. There's Mario's health right there. So now we know that the pointer for Mario's health is 806B7B40 plus 380. So we're going to go to the GCT codes, and we're going to make a new code called health. And we're going to go ahead and look at the USB Gecko code list at 48. which is the load into pointer, which means we want to load the pointer address, and then the next code will manipulate the actual address. So, I've already got the code created on the sidelines. So 48, and then you fill the rest of it up with zeros, says we want to use the pointer address 806B 7B40 as the primary pointer address. Awesome. And then we want to use the 14 prefix code, which says to use the pointer offset, PO meaning pointer offset and BA meaning base address. So we're going to use 14 as the prefix and 380 as the offset, because the pointer search is telling us to use 380 as the offset. So I've already created this code. I'm going to copy it, and we are going to paste it like so. Now, there's one more code that you have to do. Usually when you're doing pointers and offsets, you have to reset it. And if you read the documentation, it says to use the following code, E0, and then pad the rest of it with zeros, as well as 8000, 8000. And this is going to reset whatever pointers when the code is done executing. So I'm going to go ahead and we're going to leave this world, and we're going to verify that that this is the actual pointer we're looking at, and then make sure that this code is going to work. Alright, we've entered a new world, and we know that this following address, when we go to the memory viewer, is going to lead us to where the pointer address is. So this is going to be the pointer address, and that's going to point to another RAM address, and we're going to take that RAM address and add 380 in hex to it. So where's my calculator? I'm going to clear all this, Control V to paste, and we're going to add 380 in hex, and it's going to lead us to a new address, Control C, and we're going to go back to Weird, and we're going to put this in the memory viewer, and notice, it looks like it's the right value, so we'll go to the pointer search, the poke window, Control V to paste, and we'll make this 2, and we'll poke it, and hey, look, it worked, which means we did find the valid pointer. So we can go to the GCT codes, which if you really don't want to get into all of this, cheat code hacking and all this jazz, you can go to the USB Gecko forums. They have a whole community, a lot of really cool people that know a lot more about this than I do, so really don't try to bombard me with a lot of questions about this. I'm still doing a lot of learning. Go to the USB Gecko forums, because there's a much bigger community of Wii console hackers than there are on the BSOD forums. So we've got the code in place. So 48 prefix tells us that we're going to be using a pointer, and we're setting the pointer as 806B7B40. The 14 prefix code says to add the offset of whatever value. In this case, 380. It's telling us to use 380. So we set that to 380, and we want to set the maximum value to 3. 3 is too normal. Let's make that 6. And then we have to use the E0 code to actually reset the pointer offset so it doesn't crash the console. So let's go ahead and enable this code and hope to God once we hit apply it doesn't crash. Hey, look, and it doesn't. So you know what? I'm going to go ahead and just, without any editing magic, I'm going to go to the observatory again. I'm going to go to a completely new world, and I am just going to get hurt and see how badly I can get my ass whipped, because I know a lot of people claim that a lot of videos on the internet are fake these days, and I really hope through BSOD you've gained a little bit more faith through the actual legitimate hacking communities and a lot of the hard work that they're doing. And I'd like to thank everyone on the USB Gecko forums, as well as the USB Gecko team, for creating these wonderful tools and utilities that none of this would be possible without. So I'm going to run around, see what I can do to get hurt. And I'm not getting hurt. This code has told the we found the pointer address, which leads and the offset, and we've locked it
to a maximum value of 6. So essentially, now we have unlimited health. Now you can also affect characters, animations, how many coins you have, star bits, but there is a lot to actual Wii RAM hacking. This is just going to be the basics. I hope I really inspired you guys to be a little bit more insightful with what you guys want to do with your Wii. And I'll put a lot of information about the discrepancies of what ranges of RAM you can and cannot access in the show notes, and I'll try to put as much in the show notes as I can. I'm really hoping that I'm not running out of time on this. This segment has been kicking my ass, so for now I'm just going to say, you know what, have fun and good luck.